got a question here from Brian Watt from Phoenix, Arizona. He says, Greg, why does the space station have to be in a specific orientation in order to dock the shuttle or resupply spacecrafts? This is a really good question and not easy to explain quickly, but I'll try to do my best. Basically what's happening is, the orbital mechanics that's going on when you fire thrusters with a spacecraft have kind of a strange effect when you look at what the motion is between two spacecraft that are near each other. So, for example, if two spacecraft are right behind each other in the same orbit, and the one behind fires thrusters to move forward, what's going to happen really is that spacecraft's changing its orbit, and the new orbit is going to be an ellipse with a higher apogee, the furthest point away, halfway around the orbit. From the time of the thruster firing, the orbit's going to be a little bit higher. And so what's going to happen is, 45 minutes later, basically, at this altitude, what's going to happen is that spacecraft would move up rather than forward toward the spacecraft it's trying to catch up with. And also, since that orbit now is a little bit bigger, it takes longer to go around, and actually it'll fall behind. So thrusting forward results in floating up and falling behind, which is very counterintuitive, and a lot of the orbital mechanic effects are kind of like that. Now, those are the things that happen in the plane of the orbit, but out of the plane it's something completely different. If you fire a thruster to move the spacecraft out of the plane of the orbit, what happens is it kind of creates an angle between the two orbits, one of the first spacecraft and one of the other. And two orbits that are at an angle with each other, they cross each other twice. One, per orbit. So what would happen is the spacecraft would move out of the orbit to the side, and then half an orbit later it'd come back and cross over again, go to the other side, and then half an orbit later come back and cross again. So these are kind of weird things to take into account when you're trying to manually fly a rendezvous or even automatically fly a rendezvous. The in-plane motions and the out-of-plane are different effects from each other. But there's a couple of places that you can be relative to other spacecraft where you could stay for a while and have it not cost you fuel. For example, if you're below another spacecraft and you're trying to rendezvous with it, but you want to stay there for a while, if you're below, in other words, closer to the Earth, you're in a different orbit. You're in a different altitude. You're in a different orbit, and that orbit, takes a different amount of time to go around, and you have to apply constant thruster firings, not constant, but you have to keep firing thrusters to keep yourself there. So that costs you energy. One place for sure you can stay relative to another spacecraft and not have it cost you any energy to stay there is right in front or right behind in exactly the same orbit. And so these are really good places to approach from, because if something goes wrong, or when the shuttle approaches, if something goes wrong, or you want to check that everything is right before you finally do your final maneuver to come in, you can have time to stay in that place for a while and not have it cost you a lot of fuel to stay there. So that's one of the main reasons the shuttle approaches from that side. Theoretically, you could approach from any angle. And for other reasons, it's helpful, if you can stay in the plane, in the orbit plane, you minimize, coupling between axes. Other factors have to do with firing thrusters that might impact parts of the spacecraft. For the space station with solar arrays, we don't want to impact the arrays with the thrust exhaust, the plumes from the thrusters. So a lot of things combined, but essentially it helps to keep things in the orbit plane, and especially in the front and in the back.